This is the first of 3 videos covering verifying trigonometric identities. These are one of those topics in math that you really need to do a large volume of problems that each one might have a different algebra trick or a different trig identity that you have to use, and it's only through a large number of practice problems that you start to really see the patterns. So I've listed out some hints for verifying trigonometric identities, but basically to me, it's all about the algebra. I'm always looking to see what kind of algebra has to be happening that moves me from the left side to the right side. Am I going from a fraction to not a fraction? If I am, then that means that something has to cancel out and simplify the fraction. Am I going from multiple terms to a single term? What has to happen algebraically for that to occur? So I'm always thinking about the algebra, and especially with the more difficult problems, I like to think about side work. I like to think ahead of time about what needs to happen. So you'll see me do some side work on the side as well. Side thoughts. All right, so let's verify. We'll start our first identity, tangent of alpha over secant of alpha. We want to show that that is going to be equal to sine of alpha. When doing these identities, you always want to start on one side and then show that it's equal to the other side. This isn't something where you're working two sides of an equation. There's no multiplying both sides by secant here. We're starting on one side and showing that it equals the other side. I recommend that you start with the side that's more complicated, especially if there is an argument that's more complicated. I would start with that side because it's a lot easier to tear down an argument than build it up. Here, everybody's argument is alpha, so I would start with the side that is more complicated, which would be the fraction side. So here's where I'm going to pause and think, well, algebraically, what has to happen? I have a fraction on the left, and then I end up without a fraction on the right. So that means that something has to cancel out to eliminate that fraction. Another good idea with identities is to write things in terms of sine and cosine instead of the other trig functions. So that's where I'm going to start. I'm going to start with my left-hand side. So here's my abbreviation, LHS, left-hand side. And tangent can be rewritten as sine of alpha over cosine of alpha. And secant can be rewritten as 1 over cosine of alpha. Okay, well, let's simplify this. We can simplify this complex fraction by multiplying each of the terms by the LCD, which is cosine of alpha. And when you're writing these proofs here, you want to write it in a vertical format. Don't write it horizontally. It might be helpful to put those cosines over 1, and we see they cancel in the numerator, they cancel in the denominator. This gives us sine of alpha over just 1 in the denominator, which we know is sine of alpha, and that is our right-hand side, which is what we wanted to get to. Anytime you end a proof, you want to indicate that you're done by either putting a little filled in rectangle, or you can use the letters QED, which are Latin for quid erat demonstratum, which just means I demonstrated what I said I was going to. All right, let's try a few more. We want to verify that sine squared beta divided by cosine of beta is equal to secant of beta minus cosine of beta. So I think about what's happening algebraically. I have a fraction on the left side, but not a fraction on the right side, so that means something has to cancel. I also notice that I have a single term, that single fraction on the left, but I have multiple terms on the right. So algebraically, the only way that this can happen would be if I had multiple terms in the numerator, broke it up into two separate fractions, so that would give me my two separate terms, and then simplify each of those fractions. So that's kind of my idea. All right, let's start with this left-hand side. As again, it's a lot easier to break down a fraction than build up a fraction. All right, so now I got to get multiple terms in the numerator. So what identity do I know that involves sine squared? Don't go to power reducing here. You want to use your Pythagorean identity. So here's some side thoughts. All right, we know that, and I'm not using good notation because they're just side thoughts. I know that sine squared plus cosine squared is equal to 1. So that means that sine squared would be equal to 1 minus cosine squared. And I like that as a substitution because there's my two terms. And notice it has a minus sign just like I have on the right-hand side. So I feel like this is getting me two things. All right, subbing that into our numerator, 1 minus cosine squared beta over cosine of beta. See, I'm back to my good notation since I'm actually writing the proof. Next, we're going to break this up into two separate fractions. And simplify. But I'm also going to pay attention to my right-hand side. What am I trying to get to? Well, I want secant minus cosine. So that 1 over cosine, that's secant. And then cosine squared divided by cosine is going to leave us with cosine to the first. And there is our right-hand side. And my little box to indicate I'm done. One more in this first part, don't worry. There's 6 more in the other two parts combined. We want to show that secant to the fourth minus tangent to the fourth divided by secant squared plus tangent squared has to equal secant squared minus tangent squared. Well, there's a whole lot of secants and tangents happening here, so I would feel the need to just leave everything in terms of secant and tangent and not switch it all to sines and cosines. I'm going to think algebraically about what's happening here. I have a fraction on the left, and then I don't have a fraction on the right. That means that my fraction has to simplify in some way. I also notice that, it's a single term on the left, technically, because it's one fraction, and multiple terms on the right because of the minus sign, but I'm not so worried about that in this example like I was the previous example because I already have multiple terms in the numerator of my fraction. So I feel like, okay, I already have those multiple terms. I'm thinking I need to simplify this fraction, but this isn't a basic fraction. This has multiple terms. This is like a rational expression. So this is something that we actually want to factor. And I'm going to write some side thoughts over here because factoring expressions with trig functions in it are sometimes hard for people. So what I'm going to do is I'm going to take that left-hand side and I'm kind of going to strip it down and lose the trig words. This is secant to the fourth minus tangent to the fourth over secant squared plus tangent squared. And I like to do this a lot with trig because sometimes it can be hard to see the trig through the algebra through the trig. All right, well, there's no simplifying straight down and like canceling out here, right? We can't do that because the plus or the minus signs. So we can't just use exponent rules and subtract exponents. Instead, we're going to have to factor. So that numerator, s to the fourth minus t to the fourth, that's the difference of two squares. S squared plus t squared times s squared minus t squared. And then in the denominator, s squared plus t squared can't be factored because it's a plus, so there's no sum of two squares. So I'm left with this, but now I notice, hey, I got a common factor on the numerator and denominator that can be canceled. leaving us with just s squared minus t squared, which represents secant squared minus tangent squared, and you'll notice that's our right-hand side. Now that we have a plan of action, let's actually write a nice proof. These side thoughts, that's not good enough for a proof. All right, so we're starting on the left-hand side, and we're going to factor that left-hand side into secant squared theta minus tangent squared theta times secant squared theta plus tangent squared theta. And our denominator doesn't factor, but I'm going to put it in brackets. I always like that when I'm simplifying rational expressions. It reminds me that I'm either canceling the whole factor or none of the factor. And now I see that I have a common factor that can be canceled. And we're left with secant squared theta minus tangent squared theta, which is our right-hand side, and we're done. Be sure to watch the other videos. As I said, these identities are something that you need to practice a whole bunch of so you start recognizing the algebra techniques that you need to apply.